Hello everyone, welcome back to my channel. Today we would be discussing the solutions for the paper 2 of the November 2021 attempt, and obviously it's the HL paper. So let's start with the first question. So obviously first question contains a lot of parts. So let's discuss each part individually. So we have a 4.406 gram sample, the total weight of the sample, that only contains carbon, hydrogen and oxygen, and it was burned in excess air. So there was a complete combustion. Now after this combustion we received 8.802 grams of CO2 and 3.604 grams of H2. Using this data we have to find out the empirical formula of this compound. So let's start. Firstly, let's try to find the number of, moles of carbon in the compound. So, moles of carbon will be equal to the moles of CO2. Why is it so? Because all of the carbon that is present in the compound, that got shifted to the CO2 because we are externally just applying the oxygen. So, obviously, moles of carbon in the CO2 will be equal to the moles of carbon in the original compound. So, it would be 8.802. This is the molar mass. This is the mass of CO2. We have to divide it with the molar mass, that is 12 plus 2 times 16. Upon simplification, we would get a value of 0.2. Similarly, we have to find out the moles of hydrogen. This would be twice the moles of H2O. Why is it so? Because every molecule of H2O contains 2 atoms of hydrogen. So 1 mole of H2O will contain 2 moles of hydrogen. So using that analogy, we can just write this. So 2 times moles of H2O would be 3.604 divided by the molar mass, that is 2 times 1 plus 16. Again, upon simplification, we will find the value as 0.4. Let's try to find out the weight of oxygen in compound. So this is the weight of oxygen in the original compound. This will be equal to the total weight minus the weight of carbon and hydrogen. So total weight is 4.406 minus the weight of carbon, that is 0.2 times 12, minus the weight of hydrogen, that is 0.4 times 1. So yeah, upon simplification, we will get a value of 1.6. Now also let's try to find out the moles of oxygen. This would be weight of oxygen divided by the molar mass, that is 0.1. Now we have to find out a simple whole number ratio between the moles of carbon, moles of hydrogen and moles of oxygen to find out the empirical formula basically. So simplest whole number ratio. And this should be done between carbon is to hydrogen is to oxygen. Let's put in the value 0.2 is to 0.4 is to 0.1. Obviously, you can see like if you multiply 10 with each of these, each of the ratios, then we'll get 2 is to 4 is to 1, which is probably the simplest whole number ratio. So yeah, it's 2 is to 4 is to 1. So from here, we can say that the empirical formula is C2H4O. So that's the answer to the first part of this question. Moving on to the second part, we have to determine the molecular formula of this compound. The molar mass is 8.812. So let's start to find the empirical formula mass, that is the molar mass of the empirical formula. This would be 2 times 12 plus 4 times 1 plus 16. If we add this up, we will probably get 44. Yeah. Okay. Now we have to find out N. N is basically your molar mass of compound divided by the empirical formula mass. So it's given as 88.12, the molar mass, and the empirical formula mass is 44, which approximately gives you a value of 2 for N. Now we know N, so the molecular formula would be this C2H4O whole N, so it would be C2H4O whole 2. So finally we are getting C4H8O2, which is the molecular formula, and that's the correct answer to this question. Yeah. Now going on to the next part, we have these mass spectrums. We are given 3 of the mass spectrums: the spectrum A, spectrum B and spectrum C. And the question starts like this: the following spectrum show the infrared spectra of propan-1-ol, propanal and propanoic acid. So firstly, we have to identify each compound. We have to obviously use the range from 1700 to 3500 centimeters, and obviously we have to use section 26 of the data booklet. So I have the section 26 here. So which ones are important to us? This one is important to us: OH of carboxylic acid with hydrogen bonding. Then this one is important: OH of alcohol and phenol with hydrogen bonding. This is important: aldehyde ketone carboxylic acid ester, C double bond O. So yeah, now let's try to analyze it. For the first one, I've already marked it here. You see there is a big dip here between this 3200 to this part, to 3600. So obviously what does this signify? Yeah, this signifies this thing, the alcohol phenol with hydrogen bonding. And is this dip broad? Yeah, this dip is kind of broad. It is broad. So first one, it is obviously propan-1-ol. And if you check for the the aldehyde part, we won't find any dip in the aldehyde part. So you would see there should be a dip between 1700 to 1750 for a C double bond O. But yeah, there is not really a big dip here, anywhere between 1700 to 1750. So obviously the first one is propan-1-ol. Identity is propan-1-ol. Reasoning is dip at, so what was the range again? 3200 to 3600. Or I can write it in this way too: broad dip at 3200 to 3600. That's the reasoning for the part A. Now part B, here again you would see a very big broad peak here, and there's also another significant peak here. Here this mark is 100, 1, 2, 3, 4, 5, 6, 7. Yeah, so one peak at 1700 and another broad peak around 3000. So let's just check here. So for carboxylic acid, we should have a broad peak from 2500 to 3000. Yeah, this is correct. I can see a very broad peak here. This one specifically. That's correct. And it should also contain the C double bond. So there should also be a dip at 1700 to 1750. And I can see that dip. I can see a dip here. So yeah, with this two information, I can say obviously this is the carboxylic acid or the propanoic acid. What would be the reasoning? Again, broad dip at 2500 to 3000. This confirms the OH of the carboxylic acid. And another dip at 1700 to 1750. This confirms the C double bond of the aldehyde group. Not exactly the aldehyde group, I mean the C double bond of the carboxylic acid group. Last we are just left with obviously propanol. The last one should be propanol, but let's just check here. Propanol, we should have one dip at 1700 to 1750, and we can see there is like a prominent peak here at exactly 1700. Yeah, that is the propanol, and the reasoning will be dip at 1700 to 1750. That's the answer to this question, to the part C. Now moving on to part D, we have to predict the number of 1H NMR signals and splitting pattern of CH3, each for propanone and propanol. Firstly, let's try to understand how many signals will be generated. So this is your propanone and this is your propanol. In propanone, if we see, there is actually a small, you can see this is a line of symmetry. Basically, these two carbons are equivalent to each other, or the hydrogens here are equivalent to each other. So both of the hydrogens will generate exactly the same signal. So yeah, total number of signal produced here would be 1. And for propanol, you see there is no plane of symmetry. There is no symmetry technically between like in this compound. So this hydrogen, this hydrogen, this hydrogen, these three hydrogens are completely different from one another. So they will generate different signals. So I can say 3 different signals will be generated: one for this hydrogen, one for this hydrogen, and one for this hydrogen. So in propanol, we will have total of 3 signals. Now let's try to understand the splitting pattern of CH3. So splitting pattern of CH3 means we need to just find out the splitting pattern of the CH3 and for these two. Let's start with propanone. For propanone, what happens is you have 2 CH3 groups, but they are equivalent to each other. So splitting pattern will be same in both of them. Now how to find the splitting pattern? We use the N+1 rule. So what is this N+1? You need to find the splitting pattern of CH3. To find the splitting pattern of CH3, you have to check the number of hydrogen or the number of protons attached to the next group. So here, this is the group which we for which we have to find the splitting pattern. So we need to check the hydrogens here. The number of hydrogens here is 0, obviously because it's C double bond O. So N+1 becomes 0 plus 1. N is basically the number of hydrogens on the adjacent atom. So this becomes 1 for this CH3 of propanone. Obviously, if you do it for this CH3, again you will get 1 because this is the adjacent carbon, and obviously there's no hydrogen attached to it. So 1. So 1. If you get N+1, this value is 1. Then it's a singlet. Now let's try to similarly do this for propanol. For propanol, see, this is your CH3 group, and this is the group which is beside CH3. So we have to identify the number of hydrogen atoms on this carbon or this group. So obviously clearly it's 2. So your N+1 will be 2 plus 1, that is 3. If you get this value as 3 though, this will be a triplet. So that's all about part D. Now part E is we have to use section 28 of the data booklet, which is here, and we need to identify which fragment is responsible for the M by Z of 31 in the mass spectrum. So go here, 31 corresponds to CH3O. So yeah, the fragment is CH3O. You might also include a positive sign here because in mass spectrum generally the fragments, they are all cations. Yeah. So that's the answer to part E. And with this we are done with question 1, and so let's move on to question 2 now. So here it says electronic transitions are related to trend in periodic table. Part A, explain the general increase in trend in the first ionization energies of period 3 elements from sodium to argon. So how to answer this? So basically there can be 2 points. What happens is when you move from left to right of a period in a periodic table, the number of protons, or you can say that the nuclear charge, it will increase. So if the nuclear charge increases, what happens is the electrons, they will be pulled towards the nucleus with a greater force. That's number 1. Second is the electrons will occupy the same shell in a period. So as the force of this attraction by nucleus increases, obviously as I just told you, this they will be attracted more strongly by the nucleus, and hence it will be difficult for us to remove the electrons from the outermost shell of this atom. So the ionization energy will increase. So let's just write it here. The first point would be on moving from left to right of a periodic table. Just to write it like this, of a period, the number of protons and nuclear charge increases. So what happens if the nuclear charge increases? So as the electrons occupy the same shell, the force of attraction by the nucleus increases, and hence ionization, or maybe you can just include the word forced ionization, energy increases on moving left to right of a period. To right of, we are specifically asked for period 3, so we can just write period 3 here. So going to part 2, sodium emits a yellow light of frequency 5109 and 10 to the power 14 Hz when electrons are in transition from 3p to 3s orbitals. We have to calculate the energy difference between these two orbitals using section 1 and section 2. So here is section 1 and section 2. Basically section 1 contains some of the relevant equations which you can use in your problem. So here we would need this equation, E equals h mu. This relates energy to the frequency, and section 2 gives you the value of h, that is the Planck's constant. So Planck's constant is here 6.63 times 10 to the power minus 34. So this energy difference, or delta E, this would be h mu. This would be equal to h mu. So value of h is 6.63 times 10 to the power minus 34. The unit of h is joule second, and frequency is 5.09 times 10 to the power 14 hertz. Hertz is equivalent to second inverse, so I can just write it second inverse. So if we multiply this, we will get the value of 3.37 times 10 to the power minus 19 joules. This is the energy difference delta E, and this is the answer to this question. So with this, we are, I guess, done with question 2, and we will move to question 3. So here in question 3, it says white phosphorus is an allotrope of phosphorus and exists as P4. It describes the Lewis structure of P4 containing only single bonds. So P4 means this phosphorus will contain 3 bonds. Obviously, phosphorus is from the nitrogen family. So what happens? Nitrogen can form 3 covalent bonds and it can still have a lone pair on itself. Same for phosphorus, it can form 3 bonds and it will have 1 lone pair on itself. So if you try to draw the structure, it actually comes out like this. It's there in any of the standard textbooks. One phosphorus will be at the center, one on top, one here, and the last one here. So there's the first one here. You see this, the central phosphorus has 3 bonds. Similarly for the outer phosphorus, one here, one here. So outer phosphorus also has 3 bonds. If I connect here, you will see that all of the phosphorus makes 3 bonds each. Now we have to add the lone pairs. There would be 2 lone pairs on each of the phosphorus atoms. Because again, it's from the nitrogen family, so the bonding would very much be similar to that of nitrogen. So this becomes the Lewis structure of P4 molecules. Now the next part, write an equation, reaction of white phosphorus with chlorine gas to produce PCl3. So yeah, go like this. P4, it's a solid, plus Cl2, it's a gas, gives you PCl3, which is again a liquid. Now we just have to balance it. To balance it, just balance the phosphorus. So we add a 4 here, so it becomes, chlorine becomes 12. So just multiply this with 6, and we are good to go. We have the reaction, and it's completely balanced. Next question is, you have to deduce the electron geometry and molecular geometry using VSEPR theory and estimate the Cl-PCl bond angle in PCl3. So yeah, again, when we are working with phosphorus, if again for PCl3, phosphorus will have 3 bonds with chlorine and 1 lone pair. So I can say total number of electron pairs around phosphorus, this will be equal to 3 plus 1. 3 bond pairs and 1 lone pair. This is 4. If your number of electron pairs around the atom is 4, we can say that the hybridization is sp3. If the hybridization is sp3, the electron domain geometry will be tetrahedral. So you have to find out the molecular geometry. So if your hybridization is sp3 and you have 1 lone pair, then the molecular geometry becomes trigonal pyramidal. So yeah, you just replace the top group of sp3. So sp3 basically looks like this, and you will have a lone pair on top. Basically, again, if you just look at the 3D structure, it looks like a trigonal pyramidal. So molecular geometry will be trigonal pyramidal. And we have to estimate the bond angle. So for tetrahedral, your bond angle is somewhere around 109 degrees. So you have to write a bond angle less than that because of the lone pair. Why is the angle less than 109? Because of the bond pair and lone pair repulsions. So what happens is, lone pair will repel these bonds and the bond angle will become smaller than usual. So it will be, so any value less than 109 will be accepted. Better to choose a safer value of around 104 or 105. So yeah, bond angle, let's just assume it as 105 degrees. It's probably the best guess here. Now in part 2, we have to outline the reason why PCl5 is non-polar while PCl4F is polar. Again, it's pretty much simple. We just have to draw the structures properly. So PCl5, the hybridization here, P is attached to 5, around phosphorus there are 5 bond pairs. So what happens for 5 bond pairs? We have sp3d hybridization. So for sp3 hybridization, we have trigonal bipyramidal type geometry. So how does it look like? It looks something like this. It is one plane, and you have Cl on top and bottom. So here what happens is, chlorine is more electronegative than phosphorus. So obviously you can say chlorine will have a delta negative charge, while phosphorus will have delta positive. So dipoles will be directed in this direction. One on top, one here, another one here, another one here, another one here. So if you check closely, then the dipoles will cancel out. This dipole will get cancelled out by this dipole. And if you can do a vector sum here, it is basically this case. Where you have like a 60 degree between each of them. So if you can do a vector sum, you will also find that these 3 dipoles will also cancel out. So if the dipoles cancel out, the molecule becomes non-polar. Or if a molecule has a little bit of dipole moment uncancelled or unbalanced, so we can also call it a polar molecule. In this case, clearly we can see that all of the dipoles are cancelling out, so it's a non-polar molecule. So outline why. First reason is the dipole moments cancel out, or I can write it like this: the individual PCl dipole moments, maybe just use this direction, use a symbol, cancel out. The second reason is this molecule is symmetric. Obviously this molecule is symmetric, it has a point symmetry, so it's symmetric. So these are the 2 reasons why PCl5 is non-polar. Mean is obviously the first reason. Second is PCl4F. Let's try to draw it. Again, it will have this sp3d hybridization, and the structure would be this trigonal bipyramidal. So this is the plane. Let's put fluorine on top and let's put chlorine on bottom. What happens is, in this case again, there would be dipole moments. So this we will be directed in this directions. one will be directed towards fluorine, and one will be directed towards chlorine. Now what happens is these three dipole moments that are there in the spleen, they will cancel out 100%. They will cancel out again because as I told you, there would be 60 degree and all of them are in each in a similar magnitude. So if you do a vector sum, they will cancel out. But check for fluorine and chlorine. What happens is fluorine is more electronegative than chlorine. So what happens? Fluorine will like pull electrons towards itself. Will form it'll have a delta minus charge, and chlorine will also be delta minus charge. But the magnitude of delta minus charge on fluorine will be more because it's more electronegative. So the dipole moment directed towards fluorine will be greater in magnitude as compared to the dipole moment that is directed towards chlorine. So what happens? There is a little bit of unbalanced dipole moments in the PF dipole. So that's why dipoles won't get cancelled out completely. There would be a little dipole moment left which is unbalanced. So hence PCl4F is polar in nature. So we can just write it like this. PF bond polarity is more than PCl bond polarity. Hence dipoles do not cancel out. There can be a second reason: molecule is unsymmetric, or you can say it's not symmetric. That's all about this question. Now let's move on to part C. So here in part C, we have an equilibrium that exists between PCl3 and PCl5. Where is this reaction? It's a reversible reaction. So we have to find the standard enthalpy change for the forward reaction. So delta H naught, or delta H, is basically delta, or like we can just use this summation delta HF naught of products minus summation delta HF naught of reactants. For products, we just have PCl5, so this would be minus 398.9. And for reactants, we have PCl3 and Cl2. For PCl3, it's minus 306.4. And for Cl2, just remember, anything in its standard state, the enthalpy of formation becomes 0. Because Cl2, you can naturally obtain Cl2 from the environment. Like you can naturally obtain chlorine from the environment in the Cl2 form. So you don't have to give energy for that. So enthalpy of formation of Cl2 becomes 0. Upon calculation, you will find that delta H value is minus 92.5 kilojoule mole inverse. This is delta H naught. This is the answer to the first part of this question. You can also write it in this way: 10 cube joule mole inverse. That is also okay. That's also all right. In the next part, you have to calculate the entropy change delta S. So it'll go similar to the previous one. So our delta S would be summation of delta S of products minus summation of delta S of reactants. Product was PCl5, so 364.5. Reactant was Cl2 and PCl3, so minus 311.7 plus 223. So upon calculation, we will find delta S as minus 170.2. The unit will just be equivalent to this. So joule, Kelvin inverse, mole inverse. This is our delta S, and this is the answer to this part of this question. Next part is we have to find out the Gibbs free energy change of this reaction at 25 degrees Celsius using the section 1 of the data booklet. So what do we get from section 1? We basically get the formula of delta G as it is. So it will look like this. This is the formula that you will obtain from the section 1. Delta G is equal to delta H minus T delta S. So delta H we obtained as minus 92.5 kilojoule mole inverse, while delta S is 170.2 joule Kelvin inverse mole inverse. Now when we are working with delta H and delta S, you either have to convert delta H to joules, or you either have to convert delta S to kilojoules. Better if we convert delta S to kilojoules, because we would be multiplying it with temperature. So we can just write it as 0.kilojoule Kelvin inverse mole inverse. Now we can do this calculation. Put delta S as this, and delta H would be in the kilojoule form. It would be minus 92.5 minus this would be temperature is given as 25 degrees Celsius, so we have to convert this to Kelvin. So 273 plus 25 times delta S as I told you, would be taking as 0. No, 0 is negative of 0.1702. In both the cases, you will see that the unit becomes kilojoule mole inverse. Now if we simplify this, we will finally end with minus 41.78 kilojoule mole inverse. This should be the correct answer to this question. And if you want to round it off to 3 significant figures as of IB rules, it would be minus 41.8 kilojoule mole inverse. That's the answer to this part 3. In the next part, you have to write the equilibrium constant key for the reaction referring to section 1. So again, we have to use a formula from section 1, that is delta G is equal to minus of RT ln K. That's the general formula, but here in this case, you have to put delta G in the form of units if you want to use R as 8.314. So let's just do it. So minus 41.8 times 10 cube. This converts the kilojoules to joule mole inverse. R becomes 8.314. Temperature is, again, you have to convert it to kelvins, times ln K. If you simplify this equation, you will finally end with the value of K, that is 2.12 times 10 to the power 7. So as K has such a good, big value, the reaction will be mostly forward based. Next is we have to write the expression Kc for this reaction. So this is the reaction. So Kc is obviously product by reactants. So Kc will be equal to PCl5 by Cl2 times PCl3. And the next question is state for the reason the effect of increasing temperature on the position of equilibrium. So whenever we have a temperature involved in equilibrium, in an equilibrium state, we have to check for the delta H or the enthalpy. So delta H in this case for this reaction is negative. So it is an exothermic reaction. For exothermic reaction, if you increase the temperature, what happens is the reaction shifts to the reactant side. So that's just the answer to this question. So delta H is negative for this reaction. So it's an exothermic reaction. For an exothermic reaction, increase in temperature shifts the position of equilibrium to the reactant side. That's another part. Now let's move on to part 4. So we have one chloropentane that reacts with aqueous sodium hydroxide. Treat the type of reaction. Obviously, this is like a halogen or a haloalkane reacting with a base. So it's obviously a nucleophilic substitution reaction. Or you can also say it would be an SN2 reaction because this chlorine is attached to a 1 degree carbon. So it's a nucleophilic substitution reaction. Or we can say it's a SN1 reaction. State the role of hydroxide in this ion. So hydroxide OH minus, as it has a negative charge on itself, it's a nucleophile. OH minus ion acts as the attacking nucleophile. Yeah, that's the correct answer to this question. Now we have to suggest a reason why one iodopentane reacts faster than one chloropentane under the same condition. It also asks you to use section 11 for consistency, but it's really not required here. So iodine atom is a lot bigger as compared to the chlorine atom. So because of this bigger size of iodine, the Ci or the carbon iodine bond enthalpy is much lower as compared to CCl. This lesser bond enthalpy gives us an idea that this bond will be broken more easily, and hence this reaction can proceed faster as compared to 1-chloropentane. So here it goes. Ci bond enthalpy is much lesser than CCl bond enthalpy. Yeah. Because of the bigger size of iodine. So lesser bond enthalpy means the bond can be broken more easily, and hence one iodopentane reacts faster than 1-chloropentane. 1-chloropentane. That's the correct answer. Now the next part. This reaction was repeated at a lower temperature, so we have to sketch the labeled Maxwell-Boltzmann energy distribution at original temperature T1 and a new temperature T2, or a lower temperature T2. So obviously this is a general curve. We all know this. So one of the curves will be like this. The other one, of the lower temperature one, will have a peak before it, and the peak will be much prominent. So yeah, and say this is T1, this is T2, where T1 is greater than T2. Yeah. Now we are done with question 4. Let's move on to question 5. So we have phosphoric acid S3PO4 written from 3 salts depending on the extent of neutralization by sodium hydroxide. So for this one, you have to write the equation of reaction of 1 mole phosphoric acid with 1 mole sodium hydroxide. So one of the H plus ions will be neutralized here. This is an acid-base reaction. So obviously in an acid-base reaction, water is a byproduct, and we will have a salt. Salt would be NaH2PO4. This is the reaction. Now we have to draw or write 2 equations to show the amphiprotic nature of H2PO4 minus. So here basically we have to write 2 equations that will show the acidic nature and the basic nature of H2PO4 minus. So pretty easy. Let's start with the reaction with water in both cases. H2PO4 minus aqueous plus H2O liquid. If it acts as an acid, then what happens? We'll donate an H plus ion to H2O. It will be HPO4 2 minus aqueous plus SVO plus aqueous. The next one is the basic nature. For the basic nature, again, it should be accepting an H plus. So yeah, H2PO4 minus aqueous plus H2O liquid. Here H2O will donate an H plus to H2PO4 minus. So it will become S3PO4 aqueous plus OH minus aqueous. So that's all about this part B. Now let's move on to part C. So probably I would require another page here. Yeah, done. So we have to calculate the concentration of H3PO4 if 25 centimeter cube is completely neutralized by addition of 28.4 centimeter cube of 0.5 mole per dm cube NaOH. Let's try to find out the moles of NaOH first. How would we do it? We have to multiply the concentration with the volume, and obviously convert this volume to decimeter cube, because here it's decimeter cube. So 0.5 times 28.4 divided by 1000. This will convert to 1.42 times 10 to the power minus 2 moles. This is the moles of NaOH. Now we have to write the balanced chemical reaction, or the entire complete neutralization reaction between SCPO4 and NaOH. So we'll again go like this: SCPO4 aqueous plus thrice NaOH aqueous gives us NH3PO4 aqueous plus thrice H2O liquid. Now it's kind of a stoichiometric problem. We have the moles of NaOH. We have to find out the moles of H3PO4. So let's write the stoichiometric ratio by moles of NaOH. This will be equal to 1 by 3. Now we know the moles of NaOH. We can plug in here. The moles of H3PO4 would be equal to 1.42 times 10 to the power minus 2 divided by 3, and which gets simplified to 4.73 times 10 to the power minus 3. Now the concentration of H3PO4. Concentration is moles divided by volume. Moles here is 4.73 times 10 to the power minus 3. And if you check, the initial volume was 25 centimeter cube. So to convert it to decimeter cube, so upon simplification, we'll get 0.189 mole dm cube. This is the answer to this question. Yes, that's clear. Let's move on to part D. So we have to outline the reasons why sodium hydroxide is a Bronsted-Lowry and a Lewis base. Why is it a Bronsted-Lowry base? Because NaOH can donate OH minus ions, which in turn can accept a proton that is an H plus ion. So that's why we can say it's a Bronsted-Lowry base. NaOH donates OH minus ions, or you can also say it ionizes to OH minus ions, which can accept a proton, an H plus. And we define bases as H plus or proton acceptors in Bronsted-Lowry concept. Next one is a Lewis base. So we can write it in this way. Like, obviously, what happens for Lewis base? OH minus ions can donate an electron pair for neutralization. That's why it's a Lewis base. So NaOH again donates OH minus ions, which can in turn donate an electron pair for neutralization. That's the end of this question 5. Let's move on to part 6. So biochemical oxygen demand can be determined using the Winkler method. So outline what is measured by BOD. BOD is just a basic definition. BOD is the amount of oxygen required to decompose the organic matter present in a sample of water. That is the basic definition of BOD. Now the next one is you have a student has dissolved this much amount of Na2SO3 to make 1000 plus minus 0.4 centimeter cube of solution to use the Ringler's method. Now we have to determine the percentage uncertainty in molar concentration. So molar concentration, moles of Na2S2O3. Looks so bad. Just a second. Yeah. Now looks good. Divide by volume of water, or volume of let's use volume of solution. So as it's a division case, so our total percentage uncertainty would be percentage uncertainty in the moles of Na2SO4 or the mass of Na2. Again, the total percentage uncertainty in the molar concentration. This will be the sum of the percentage uncertainty of the moles of Na2S2O3, which is basically equal to the percentage uncertainty in the mass of Na2S2O3, because you are dividing mass by the molar mass, because molar mass is a constant thing. Percentage uncertainty will be same between mass and moles, and we have to add this to the percentage uncertainty to the volume of solution to get the total percentage uncertainty in the molar concentration. So percentage uncertainty in moles of Na2S2O3. This will be equal to percentage uncertainty in mass of Na2S2O3. This will be equal to 0.001 by 0.12 times 100. This comes out as 0.081%. Second is you have to find out the percentage uncertainty in volume of solution. This will be equal to 0.4 by 1000 times 100. So it is 0.04%. So percentage uncertainty in molar concentration. In molar concentration, this will be equal to the total percentage uncertainty. That is 0.081 plus 0.04%. So we get this as 0.121%, which is the answer to this question. Now coming to the next part. In the first part, you see there is 25 centimeter cube of water, sample of water that it was treated. Treated according to the Ringler method. So step 1 is given, step 2 is given, step 3 is given. These are the 3 steps of Ringler method. So the first part we have to calculate the amount in moles of Na2S2O3 that's used in this titration. So let's do it. Moles would be, that is concentration times the volume, and we have to change the volume to decimeter cube. So from here, if you simplify this, you'll get 1.875 times 10 to the power minus 5 moles. Second is we have to find out the mole ratio of O2 consumed in step 1 to S2O3 minus used in step 3. We would need a little bit extra space. Now it looks a lot better. So we have to find out the mole ratio of O2 that's consumed in step 1 to S2O3 to minus used in step 3. I've seen a lot of students struggle with this question basically. So let's try to answer this question. And 1 mark for this question might be a little low. They should have offered 2 marks for this. Here, this is how the procedure will go. So what we need to find is you have to find moles of O2 divided by moles of S2O3 2 minus. Now let's start from step 3. From step 3 we can get the ratio, molar ratio of I2 and Na2S2O3. So why did I choose I2? Because I2 is present in the previous step. And here we have to find out the mole ratio between I2 and MnO2. Why did I choose MnO2? Because MnO2 is again there in the previous step, and we can find the molar ratio between MnO2 and O2. So firstly, from step 3 we have to write the stoichiometric ratio between I2 and S2O3 2 minus. Moles of I2 by moles of S2O3 2 minus. This would be equal to 1 by 2, because 1 is the stoichiometric coefficient of I2 and 2 is the stoichiometric coefficient of S2O3 2 minus. Now step 2, here we have to do between I2 and MnO2. So moles of MnO2 by moles of I2 This will be equal to 1 by 1, or I can just write it as 1. Now we are at step 1. Here we have to do the ratio between O2 and MnO2. So moles of O2 by moles of MnO2. This will be equal to 1 by 2. Now just observe, if we multiply these three, this is 1, this is 2, and this is 3. If we multiply these three ratios together, we will get moles of O2 by moles of S2O32 minus. So let's try to multiply it. So we're doing 1 times 2 times 3. What will happen here? We will have S2O32 minus moles of MnO2, moles of I2. Not an equal sign, it will be a product sign. O2 by moles of MnO2. This would be our left hand side, and the right hand side would get multiplied to half times 1 times half. So yeah, let's just see what can be cancelled. So MnO2, these two can be cancelled, and these two can be cancelled. So what we are left with is moles of O2 by moles of S2O32 minus. This will give us 1 by 4, and this is the answer to this question. Now let's move on to part 3. So to calculate the concentration of dissolved oxygen. So from here we know the moles of Na2S2O3, and we can just assume Na2S2O3 is a strong electrolyte. So all of the Na2S2O3 will dissociate into Na plus and S2O32 minus ions. So moles of S2O32 minus will be equal to the moles of Na2S2O3. So just plug in here moles of O2 by moles of S2O32 minus. This will be equal to 1.875 times 10 to the power minus 5. This is equal to 1 by 4. But from here moles of O2 becomes moles of O2 would be 1.688 times 10 to the power minus 6. Now we have to find the concentration of O2. This is moles by volume, so 1.688 times 10 to the power minus 6. Volume of O2, volume of the solution was taken as 25 centimeters. So we have to divide by 25 times 10 to the power minus 3 because we are converting the centimeter cube to decimeter cube. Upon solution, what we will have is 1.875 times 10 to the power minus 4 mole per dm cube. This is the answer. Let's go to the second last part of this question. So we have 3 steps of Winkler method, and all of the steps are redox reaction. Obviously, yeah, all of the steps are redox reaction in Winkler method. We know that. So we have to reduce the half equation for step 2. Step 2 is here, Mn, this one. So obviously we can say iodine from -1 is going to 0 oxidation state. So this is an oxidation. So reduction would be in between MnO2 and Mn2 plus. Let's try to do that. Gets reduced to Mn2 plus. So what happens is the oxidation state was of Mn was +4 here, and it became +2. How is it +4? So x plus 2 times -2. This will be equal to 0 for MnO2. Why 2 times -2? You have 2 oxygen. For oxygen, in most cases, the oxidation state is -2, except for peroxides, superoxides, or bonding with fluorine. So here you can get that x is +4. So +4 is the oxidation state of Mn. We don't really need this anymore, so just remove it. From +4 to +2. First, we have to do the charge balance. So here we have to add 2 electrons. You see the net charge on the left side is +2, and also on the right side is also +2. Yeah, charge is balanced. Now we have to balance the oxygen. So O2 means we have to add 2 H2O on the right hand side, and we can add 4 H plus on the left hand side to balance out the hydrogen. And this is our reduction half reaction. Just remove the charges at the end. Of course, there's the Mn+2 ion. Now, last part of this question goes like this. So we have to suggest a reason that Winkler method used to measure biochemical oxygen demand must be done at a constant temperature. So on increasing temperature, what happens on increasing temperature? Whenever you have a sample of water from a water body or something, it would be full of bacteria and microorganisms. If you increase the temperature, what happens is generally the reproductive ability of these bacteria or microorganisms that increases. So if it reproduces more, what happens? The reaction rate increases, and as a result, more and more bacteria is produced, and your BOD value will change if you increase the temperature. So generally, BOD is measured at a constant temperature. Yep. So on increasing temperature, rate at which bacteria grows. This is bacteria. Reproduces and respires will also increase, and hence the BOD value will change. So moving on to question 7, we have alkanes undergo combustion and substitution, obviously. So determine the molar enthalpy of combustion of an alkane if 8.75 times 10 to the power -4 moles are burned, raising temperature of water or 20 gram of water by 57.3 degrees Celsius. So the net heat is given by mc delta T, where m is 20, c is 4.18, and delta T is 57.3. So the unit will be joules. So Q comes out as 4790.3 joules. This is the heat that was generated while we are burning 8.74 times 10 to the power -4 moles. To find the enthalpy of combustion, we have to divide this heat with the number of moles. Okay, and also in enthalpy of combustion, it's an exothermic reaction. So heat is given out to the surroundings. So we have to put a negative sign here to compensate for that. So minus of 4790.3 by 8.75 times 10 to the power -4. This will give us a value of delta Hc of -5474605.7 joule mole inverse. So we can just convert it to kilojoules, and it will result like this: 5474.6 kilojoules mole inverse. This is the answer to the part A. Moving on to this next part, we have to formulate equations for 2 propagation step and 1 termination step in the formation of chloroethane from ethane. So obviously it's a free radical substitution. Now how do we differentiate between propagation and termination step? In propagation step, the main thing for identification is the number of free radicals on the reactant side will be equal to the number of free radicals on the product side. For example, these two steps I can say these are propagation steps. This would be C2H5 radical plus HCl. Another propagation step is C2H5 radical plus Cl2. This will give you C2H5Cl plus Cl radical. These are propagation steps. Just note that number of free radicals here was 1 and the product side is also 1. Same for this case, 1 for product side, 1 for reactant side, 1 for product side. These are the propagation steps. Now how do we identify a termination step? In a termination step, you would find that the number of free radicals on the reactant side will be greater than the number of free radicals in the product side. For example, Cl dot plus Cl dot will give you Cl2. The number of free radicals on the reactant side is 2 and product side is 0. So free radicals are getting used up. So if free radicals are getting used up, we can conclude that the reaction is coming to an end. There can be another example too. For example, C2H5 radical plus Cl radical. This will give us C2H5Cl. This is also a termination step. Yeah, we are overall done with part B. Now we have to go to question 8. In question 8, I can't just put in the diagram because I might get a copyright strike from IB. So I've kind of drawn it. This is the setup which was there. So we are measuring the standard electrode potential of zinc using a standard hydrogen electrode, that's an SHE. We have to draw and annotate the diagram to show that the complete apparatus is required to measure the standard electrode potential of zinc. Now let's try to start with the basic. So firstly, there would be a voltmeter here or an ammeter. Basically, we'll use a voltmeter because we are trying to measure the standard electrode potential. Here it would be connected. And there would be a salt bridge here to complete the connection. This will be the salt bridge. This is the salt bridge. This will be the voltmeter. So this side is zinc and this would be a solution of Zn2 plus aqueous. Here this is the hydrogen electrode, standard hydrogen electrode. So what is this thing? This is a platinum electrode. What is the solution? This is the solution of H plus ion, so H plus solution. And what is the concentration generally? The concentration of this H plus solution is generally 1 mole per dm cube. Mole per dm cube. This is the concentration. And here we pass in H2 gas. As it's a gas, we have to pass it at a specific temperature and pressure. The temperature is basically 298 Kelvin, which is the normal temperature, and 100 kilopascal pressure. Yeah, so that is all for this question 8. This diagram would be given, the one on the black, this would be given in your question. You just have to complete this apparatus and you have to annotate or label the stuffs that are present in this diagram. So yeah, that's all about question 8. Let's move on to question 9. So we have a fast moving helium nuclei. It was fired at a thin piece of gold. Helium nuclei is just the alpha particle. It is fired at a thin gold foil. It's a very thin gold foil with most passing undeflected, but a few deviating largely from their path. So just what can be concluded about the gold atom from this experiment? So most alpha particles passing straight through. This means that most of the space inside this gold atom is empty. This can be concluded from the first part. On the next part, very few alpha particles are deviating largely from their path. What does this mean? This means that the nucleus is very small and dense. That's the first thing. Second thing is the nucleus should be positively charged. If the nucleus is if the nucleus was negatively charged, they wouldn't have deviated. Nucleus would have attracted them towards itself. So yeah, there should be like a repulsion between the alpha particle and the nucleus. So we can conclude nucleus is positively charged. So first part is the nucleus is very small and dense. Second thing is the nucleus is positively charged. That's all about this part A. Now let's move on to part B. So we have to draw the diagrams of 1s, 2s and 2p. 1s and 2s, they are spheres. So 1s would be a smaller sphere, 2s will be a larger sphere. So yeah, this is 1s. This would be 2s. And 2p is a dumbbell shape. P orbitals are dumbbell shaped. Draw it like this. This would be the positive lobe. This would be the negative lobe. Yeah, that's all here. Next, we have to state the electronic configuration of copper. Copper, from the periodic table, you can get its atomic number is 29. 29, let's start. So first 1s2, 2s2, 2p6, 3s2, 3p6. 3p6, 4s2. These are the first 20 electrons and you have 3d9. But what happens is this electronic configuration doesn't hold true for copper. There is an exception. Exception is it forms 3d10 and the s orbital, just the 4s orbital just has 1 electron. So this is the electronic configuration. This is an exceptional configuration, but yeah, that's how it will look like. Next, we have to use section 3 and section 15 from the data booklet. So let me include it here. So continuing with part 3. So copper is a transition metal that forms different colored complexes. So we have a complex CuH2O6 that changes color when XlCl- is added. So we have to explain the cause of this color change using section 3 and section 15. So we really don't need the section 3 here. We just need the section 15 here. So what happens is if you check, chlorine is here, H2O is here. So chlorine is behind hydrogen in the spectrochemical series. What does this mean? This means that when chlorine forms a complex with copper, the splitting of the d orbital from the crystal field splitting, this splitting won't be large. So there would be a small splitting between the two sets of orbitals of D in which it will get split. So because of this, low energy splitting, the frequency of light that will be absorbed by this CuCl6 compound, CuCl6 complex, this energy will be low. As a result, what happens is the color will obviously change, definitely change. So yeah, that's what we have to incorporate here from the spectrochemical series. Cl minus is much lower as compared to H2O. This should be our first point. Second point is be able to split the d orbitals as much as H2O. So the splitting, the difference of energies of these two sets of d orbitals will be low. As the energy of splitting will be low, the frequency of light absorbed is decreased. That's the answer to the part 3. Now let's move on to question 10. So hybridization of hydrocarbons affect their reactivity, obviously. So question 10a, part 1, distinguish between a sigma bond and a pi bond. It's pretty easy. Sigma bond is found when you have head-on overlap between two atomic orbitals, and the pi bond is found when you have lateral or sideways overlap of the atomic orbitals. So yeah. Formed by the head-on overlap of atomic orbitals, while pi bond is formed by the lateral or sideways overlap of atomic orbitals. That is all about this part A and part B. So basically, if you have two p bonds, if they overlap in this way, a sigma bond is formed here, and if they overlap in this fashion, this will be your pi bond. This is your pi bond. Now the next is you have to identify the hybridization of carbon in ethane, ethene and ethyne. So for calculating or find the hybridization in carbon containing compounds, as I have told you have to count the number of sigma bonds around the atoms. For example, in ethane, the hydrogen, and here we have another hydrogen. So between each carbon atom there are 4 sigma bonds. Every single bond is a sigma bond. Every double bond contains 1 sigma 1 pi, and one triple bond contains 1 sigma 2 pi. So if you have 4 sigma bonds, the hybridization will be sp3. So for ethane, the hybridization is sp3. For ethene now, the hybridization will obviously change. So here you see there is 1 sigma bond and there is 1 sigma bond in the 2 single bonds. But in the double bond you have 1 pi bond and 1 sigma bond. So 1 pi bond, 1 sigma bond. So around any of the carbon atoms, let's say around this carbon atom, we have 3 sigma bonds. 3 sigma bonds mean we have sp2 hybridization. So this would be sp2. Let's do the same thing for ethyne. For triple bonds, what happens is you have 1 sigma bond and 2 pi bonds. So this is 1 sigma. There are 2 pi bonds here and 1 sigma bond here. So around this carbon there are 2 sigma bonds. 2 sigma bond means your hybridization is sp. There's another way you can, most people try to understand this. That is, if a carbon is attached to a double bond, its hybridization is sp2, and if it's attached to a triple bond, its hybridization is sp. While if it's attached to only single bonds, it's sp3. That concept I don't think is always valid, because let's say you have a carbon that is attached to 2 double bonds. What would you do in that case? In that case, you have to count the 2. If there are 2 sigma bonds around this carbon, so it would be sp hybridized. So yeah, it's a better method to follow. Now we have to go to B part 2, part 1. So you're giving a reason if but1 exhibits cis trans isomerism. So let's just try to draw this figure, draw the compound for now. Hydrogen. So will it show cis trans isomerism? It won't show cis trans isomerism, because these two groups are same. If these two groups were different, if one was hydrogen and another was CH2CH3, then it would have shown cis trans isomerism. But as both of them are hydrogen, so it cannot show cis trans isomerism. So it will go like this. It doesn't show cis trans isomerism because on carbon 1 means this is the carbon 1. Both groups are same. Attached are same. That is hydrogen atom. What type of reaction occurs when but1 and hydrogen iodide reacts at room temperature? Obviously, it's an addition reaction, and you can also say it's an electrophilic addition reaction. Electrophilic addition. Now we have to write the mechanism. So let's start with step 1. H, I have drawn this bond in an elongated manner. So see, between H and I, this is a polar bond, because iodine is more electronegative than hydrogen. So what happens? Iodine will have a partial negative charge, while hydrogen will have a partial positive charge. So this double bond, it has a huge electron density. So when this Hi atom is close to this double bond, what happens is this double bond will attack this Hi, because a double bond is basically dense in electrons. Electrons obviously will get attracted to the positive end. So yeah, they will attack this small, slightly positive hydrogen atoms, and iodine will take the electrons with itself. So we will have something like this after step 1. So yeah, we can have a lot of compounds. So this would be I minus plus. There are two cases. You can either have CH3, CH, CH2, CH3 plus. You can either have this one or you can have this. Oh, it looks so bad. Let's fix this. This is positively charged and there are two hydrogens attached to it. These two compounds will be formed. Now step 2 is easy. So we will add I minus to both of them. So I minus will just form a bond with the positively charged end. This and 3. There is hydrogen. So obviously this is 2 iodobutane and this is 1 iodobutane. This is the major product. Well, this is the minor product. So minor product will be formed like 2%, 3%, maximum up to 5%, but more than 90% will be the major product. Why is this 2 iodobutane the major product? Because after step 1, this carbocation is more stable as compared to this carbocation, because this carbocation, this positive charge is like shared by 2 big carbon groups on both sides, while here it's just surrounded by 1 carbon group. So the intensity of positive charge will be less in this case, but here the intensity of positive charge will be high. And we know higher charge means it's an unstable ion or an unstable carbocation. So unstable carbocation obviously yields the minor product. Now the last part is if this product will exhibit stereoisomerism. So if we analyze the major product, you can see, right, let's just draw the major product again. If we work on this carbon, you will see that all the 4 groups that are attached to this carbon, they are all different: hydrogen, iodine, methyl and ethyl. So this carbon is chiral. So yeah, chiral carbon, and it's marked with a star, and hence it exhibits stereoisomerism. That's all about part D. Now let's start with our part C, which is no, it's still a pretty long question. It's one of the biggest questions in the syllabus. So you have to reduce the rate expression for this reaction. Now this will be long, so I would need another page here. Yeah. So let's start with the general expression. That rate would be K times NaOH to the power of A, while C5H11Cl to the power of B. We need to find the values of A and B. Let's start with experiment 1. Plug in the values of A, plug in the values of NaOH, and plug in the values of C5H11Cl. So this will be from experiment 1. So weight becomes 2.5 times 10 to the power minus 2. Left K, this would be 0.2 to the power of A, while this would be 0.1 to the power of B. From experiment 2, we can also write it in a different way. So 3.75 times 10 to the power minus 2, there's a value of rate K. NaOH would be 0.2 to the power of A and 0.15 to the power of B. Now if we divide this, let's say this is 1 and this is 2. If we divide like 2 by 1, what we'll get is 3.75 times 10 to the power minus 2 by 2.5 times 10 to the power minus 2. This will be equal to K times 0.2 to the power of A, 0.15 to the power of B, by K times 0.2 to the power of A and 0.1 to the power of B. Upon simplification, we will find that this side is 1.5 and this side becomes 1.5 to the power of B. Therefore, B is equal to 1. Obviously, 1.5 to the power of 1 is equal to 1.5 to the power of B. So B is 1 on when we equate it. Now, let's do it for experiment 3 too. What happens for experiment 3? It's 10 to the power minus 1. K times was the concentration of NaOH is 0.4 to the power of A, and this one is 0.2 to the power of B. And power of B is 1, so I can just plug in the value of B. This is 3. So again, divide 3 by 1. What we will get here is 10 to the power minus 1 by 2.5 times 10 to the power minus 2 is equal to K times 0.2 to the power of A. This becomes 0.1 to the power of 1 divided by K times 0.4 to the power of A, and again this is 0.2 to the power of 1. Now upon simplification, what we would get is we would get we'd get 4 on this side, and not exactly 4, we'll get 2 on this side, and we'll get 2 to the power of A on this side. I guess so. Let's just do the calculations once. So these keys will get cancelled out. This is 1 by 2 and this would be 2 by 4. So 1 by 2 to the power of A times 1 by 2. This becomes 10 by so 100 by 25. This becomes 4, I guess. I guess I did it wrong. Oh, I did it in a opposite way. Wait a second. Here there was a mistake here from my end. This would be 0.4 to the power of A and 0.2 K times this is 0.2 to the power of A, 0.1 to the power of 1. So I just messed the denominator and numerator. Whatever, it's okay. You just have to find A. So upon simplification, you will find that left hand side is 2 and right hand side becomes 2 to the power of A. So A also becomes 1. So I can say that the rate equation is K times NaOH times C5H11Cl. That's the answer to this question. So that's the question answer to part 1. Let's move on to part 2. What would be the units of the rate constant? So it's a second order reaction, so we can just deduce it from here. Units of rate is mole per dm cube second. We need to find the unit of rate. Unit of concentration is mole per dm cube, that's for NaOH, and unit of, again, it would be mole per dm cube. If we simplify this, we will see that K becomes dm cube mole to the power minus 1 s to the power minus 1. This is the answer to part 2. And we have to determine the initial rate of reaction experiment 4. Before that, we have to find the value of this rate constant K, which was actually important here and I missed it. So let's just find it. So just use experiment 1, it will be easy. So 2.5 times 10 to the power minus 2 is equal to K times the concentration of NaOH is 0.2. The concentration of C5H11Cl is 0.1. So from here we can get the value. So how much do we get? So yeah, the value of K becomes 1.25 and the unit is this dm cube. I'm not using the unit here. Finally, the rate becomes 1.25 NaOH C5H11Cl. Yes, this is okay. Yeah. Now from experiment 4, we have to find out the initial rate. So experiment 4, the rate is basically, as I just wrote, 1.25 NaOH and C5H11Cl. So you have to find this rate. What is the NaOH and this concentration? NaOH is 0.6 and this is 0.25. 0.6 and 0.25. So finally, the rate becomes 0.1875 and the unit of rate is mole dm cube dm to the power minus 3 second to the power minus 1. Now we have to give a reason between the reaction of 2-chloropropane and sodium hydroxide. As we have found out that the rate of this reaction is, the order of this reaction is 2, so it would be an SN2 reaction. That's all about this part. So from the rate equation, we found the order of reaction to be 2. Hence, it is an SN2 reaction. That's all, literally all about this party. And last part is we have to discuss the reason benzene is more reactive with an electrophile than a nucleophile. So benzene, if you check benzene, it has 3 pi bonds which are conjugated. So basically benzene has a high electron density within itself. So as it has a big electron density, obviously electrophiles are basically compounds which are attracted to electrons or which are attracted to negative charge. So benzene having such a high electron density will obviously attract electrophiles more than nucleophiles. What are nucleophiles? Nucleophiles are again those compounds which are attracted to positive charge. Obviously it has more of benzene has more of negative charge as compared to positive charge. So electrophiles will be attracted more towards this benzene. So that's all. So let's write down. So benzene has delocalized or conjugated pi electrons around the ring. So the molecule has a high electron density. That is why electrophiles are attracted towards a benzene molecule and is more reactive with them. That's all about the answer to this part E. Now let's come to the last question, that is question 11. So starting with part 11, so we have 50 centimeter cube of 0.75 mole per dm cube sodium hydroxide that is added in 1 centimeter cube portions to 22.5 centimeter cube of 0.5 mole per dm cube chloroethanoic acid. Firstly, we have to find the initial pH before any sodium hydroxide was added using section 21 of data booklet. So we have to find the initial pH of this chloroethanoic acid. So this is section 21. You will get the pKa values. So chloroethanoic acid is this. It has a pKa value of 2.87. So your pKa is 2.87. So the Ka value is nothing, it's just 10 to the power of minus 2.87. So it's 1.35 times 10 to the power minus 3. Now your H plus concentration, we can directly apply this formula, is root under C times Ka. C is the concentration of this acid. Concentration is 0.5 and Ka is 1.35 times 10 to the power of minus 3. So if we simplify this, we will get 2.6 times 10 to the power minus 2 mole per dm cube. That is the concentration of H plus. If I know the concentration of H plus, pH is basically minus log of H plus. That is minus log base 10, 2.6 times 10 to the power minus 2. So this becomes 1.59. This is the answer to part 2. Now part 3 is the concentration of excess sodium hydroxide that was added was 0.362. We have to calculate the solution at the end of the experiment. So at the end of the experiment, we would assume that all of the chloroethanoic acid has reacted, and whatever left in the solution is like the OH minus ion. So I will just assume at the end of the reaction we just have NaOH or OH minus ions that will dictate the acidity or basicity of the solution. So here POH is minus log OH minus ion concentration. NaOH is a strong base, so we'll assume all of it has been dissociated. So 0.362. This comes out as 0.441. So our pH would be 14 minus POH. That is 13.559 upon simplification, and this is the answer to the part B. And in the last part, we have to obtain the neutralization curve and we have to label the equivalence point. So obviously there's a neutralization point. So the curve will initially start at 1.59. Here it's 1.59. And it will end at approximately 13.6, so somewhere here. This is 13.6. So, and in pH, there would be a big jump. So you can just draw it like this. The curve will go like here, then it will have a jump, that will have a pretty steep jump up to like 11 or 12, and then slowly increase up to 13.6. And the equivalence point, because we are using NaOH, the equivalence point will be little above 7. It would somewhere be around 8 or something, so I can just put it at around somewhere 8 pH. So this would be the equivalence point. It can be even more, also be more than 8. We have to calculate it by calculations. I mean, like using a numerical calculations, but here we can pretty much make a guess. 8, or maybe you can put 9. That will also be the correct answer. So that's it. That is the entire paper 2 chemistry HL of November 2021 attempt. So yeah. If anyone has any questions about any of my solutions here, please do point it out in the solutions. I'll try my best to respond to all of you. Also, you guys can follow me on Instagram. I'll put a link to my account in the description. Again, thank you so much for watching this video. Do subscribe to my channel, and I'll also start posting solutions of physics papers soon. That's all. Goodbye.